Hello, and welcome to episode number 22 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode, we are going to finish our discussion of file systems. And then in the coming episodes, we will be talking about virtual machines and then possibly either networking or how to design an operating system. We'll put a poll on Piazza's and you can choose which one you prefer, knowing that both of those episodes are technically already on YouTube if you choose the other one. Just a couple things today is to, if you are following along with the textbook, and again, that's totally your choice, files and directories and file system implementation are the relevant topics. And the other thing I want to remind you is don't forget about the quizzes and the reading assignments. I think one of the reading assignments is due really soon. Let me just quickly log in and check here. I don't remember the dates that I actually made them due off the top of my head because did that a while ago. While that loads, if you've been experiencing some difficulties logging into the school servers today, I just wanted to tell you not to panic. It is a somewhat scheduled outage due to some issues that needed to be solved, and hopefully you'll be able to log in today just a little bit later. Yeah, okay. So the reading assignment 2 is due on July 30th. So you've got about 3 days to finish that up, and then we can move on from that. All right, so then our OS of the day is the wonderful one that you use probably most of the time when you are doing something on your cell phone. And it seems everybody these days has a cell phone. I actually didn't get a cell phone probably until 2010 or 2011. And I feel like I probably got a cell phone because I was doing a lot of trips to different cities for conferences and just to work with different companies. And it's so easy to get lost if you've never been to Vancouver, and carrying around a bunch of printout paper maps kind of gets old. So that's why I ended up getting a cell phone, but I don't really use it for much other than maps and the odd phone call. But there are two main operating systems now for cell phones. Now, of course, there used to be a third player here, but it's not really around anymore, and that is RIM. And I mean, they still exist. You know them as BlackBerry. I know them as RIM. They used to be one of the big ones, and now they're gone. So we're not going to talk about their operating system because in a way we've already talked about it, because now, of course, BlackBerry actually owns QNX, and so they tend to use QNX or QNX-based operating systems on their equipment. But we're going to talk about Android and iOS. And I'm sure some of you out there watching actually have Linux-based phones, or maybe you have a Windows-based phone. I've seen people do shell programming on a phone before, and I can't even type on a phone, so I don't know how people do that. Anyways, so both of these OSs actually came out roughly around the same time. So Apple's iOS actually came out in 2007, and then Android came out in 2008. And both of them are Unix-like, and both of them actually are branches of their mainline operating system. So Android is a branch off of the Linux kernel, and iOS is actually a branch off of Mac OS X. But there's some pretty big differences. So Android actually predates Google owning it. So it was actually a company called Android Inc. that was acquired in 2000, or started in 2003. And they actually started building that operating system from the Linux kernel, which of course, being open source, is one of the beautiful things about it, is if you want to get the source code and modify it to fit your specific needs, you can do that. I guess it depends on whether you have the time and money to actually invest in that. Now, they did a number of changes to the operating system because they knew it was going to be run on small handheld devices which have pretty bad battery life. So they asked themselves, what kinds of things could we do to the kernel to improve the battery life? And one of the interesting things that Android does is it has a different take on how processes are managed than the main Linux kernel. So for one, they keep processes in memory. So even when you close one of those processes, or navigate away from the app, the process doesn't actually shut down, free the memory, and then the next time you tap on it, it doesn't create a new process ID, get a new process structure, and reload it. It actually keeps the processes in memory just marked as kind of inactive. And the reason for this is, as you've seen with doing fork and exec feed, there's a fair bit of system level stuff that has to happen when you create a process and when you destroy a process. And what was observed in the behavior of cell phone usage is that people open the same apps for very short periods of time, and then they close them, like a messaging service. I mean, this is something I don't even do on a cell phone. I don't use text messaging. I don't use Messenger or anything like that. I know I'm a bit odd that way, but I don't do that. But most people do use cell phones for text messaging or some kind of messaging service. I don't even know. And you get a notification that you've got a message, and so you open it up, you read the message, maybe you respond, you close the app, or you navigate away from it to something else because maybe you got a message in a different app. And you can imagine that if you're constantly opening and closing these processes, that could actually, because of the work involved with doing that, would be a fair bit of wastage in terms of battery life. So what happens in Android is the processes actually stay in memory, just kind of marked as inactive. And then that means that when they're inactive, they're not using any CPU resources. They're still using memory. And that's actually when the problem comes about. So I have kids, and my kids love to play games on the cell phone. This is actually pretty much the only thing the cell phone gets used for these days, is for playing games. And so if I pick up the cell phone to go put it on check the battery power after my kids have been playing with it, I'll see that there's like 50 different games open. And obviously those games are all quite memory intensive. So what happens is, if keeping all of these old processes, inactive processes, in memory is actually consuming your memory to a point where you can't load anymore, then they have a system to actually kill the older ones. So it's not that the processes will never be actually terminated. It's just that we are now going to wait to terminate them until either the user forces the flush, or until we start to run out of memory, and then we'll flush them. Now, there's lots and lots of other different changes that were made to the Android kernel from Linux. They have different synchronization mechanisms and so on and so forth. And Google has commented that at some point they would like those changes to be filtered back into the mainline Linux kernel, but who knows when that will actually happen. I mean, there used to be internal bets as to when certain products would get out of beta status, and it's like, it's never happening. All right. Now, iOS, again, is very similar to Mac OS X. It's a branch of it. But unlike Android, so Android is a branch of the Linux kernel, and with some modifications, a lot of things that work in Linux will actually work on an Android. But iOS is completely incompatible. So it's application incompatible with things that are on Mac OS X. So you actually have to develop separately on a separate platform, and usually it's like a virtual machine you'll develop on to develop for an iOS device. What's interesting is that Apple didn't actually support things like multitasking until the 3GS was actually released. And when we say multitasking, the older versions of the iPhone and older versions of iOS, if you wanted to like download an update and play music at the same time, or if you wanted to play music while you surfed on the web browser at the same time, that wouldn't work. You could only do one thing at a time. Now, apparently you could jailbreak the phone and you could unlock those features, but I never did that. I mean, I didn't have a 3GS. I had an iPhone 4 originally. That was my alarm clock. But as time has gone on, Apple has slowly released the ability to do some of these tasks in parallel. So it still has really restricted multitasking, but it does do some things. Like you can download things in the background while music is playing. You can do updates, and it does have some of those features. But it doesn't have true preemptive concurrency for all things that you would anticipate a modern operating system to have. And you might be thinking to yourself, well, that seems like a pretty bad idea, but is it? I mean, when I think of using a cell phone, I'm not thinking of performance. I'm not thinking about CPU utilization. And to be honest, because of the small form factor of the device, I don't even think about running multiple apps at the same time. Why would I do that? That doesn't make sense. I'm not going to have like my little tiny phone with like a little tiny web browser and then beside it my mailbox, because I can barely see the web browser when it's the full size of the phone. So it does make a lot of sense why Apple would make this decision. Now, I know iOS also runs on iPad, and iPads have a fair bit more computation power and a much larger screen. And I imagine that multitasking has been opened up a bit more on that particular hardware as a result. But for the little phones, it makes perfect sense. So I get where they were coming from. All right. I mean, if you want to know, so I technically at one point, I did have another cell phone, but let me see if I can find a picture of it. I don't know why I resisted cell phones for so long, but I did, because I just didn't see a need for it. So at one point, I even had a phone that was even simpler than an iPhone. I'm just bringing up a picture of it now. This is the phone that I had for a while too. Actually, this is the exact one I had right here. Because if you're going to buy a ridiculous cell phone, why not buy the most ridiculous cell phone you can find? So this is the phone that I had many, many years ago. This is a cell phone, and what you'll know, yes, it's shiny plastic gold, because it looks silly and it makes me laugh. And you will notice that it has no screen, and all it has is a number pad and an on-off button, and it doesn't have anything else. Because this is what I saw cell phones as. It's just like an emergency phone. So we had at one point, I think, an iPhone 4, and then this is the second phone. And again, just as an emergency. And you might be like, well, how do you remember phone numbers and stuff? And what's really interesting about this funny little phone here is in the back. So if you were to flip this over, on the other side, there's actually a little door that opens. And inside the door is a paper book and a pen where you write phone numbers down. Now, advantages of this particular device is you don't have to worry about data overages. You don't have to worry about anything like that. And it has an absolutely wonderful battery life, because the only thing that you can do with this phone is make phone calls and receive phone calls. So, yeah, it was kind of fun. Anyways. So if there's anyone out there who's looking for something that's a little simpler to simplify their life, yeah, you can look at these phones here. They're kind of fun. Maybe not shiny gold, but there you go. All right, so where did we leave off in our last episode? So in our last episode, we were talking about implementations of the physical file system, and in particular, we talked about how the inode was laid out. We talked about how the disk data blocks were actually laid out. So just going back to some of those images there. Just trying to find a good picture. So what we've got is we have subdivided the disk into a bunch of blocks. Now, the disk itself can only do sector-based addressing, but sectors are 512 bytes on this disk, and so if I was doing on-demand paging, then what's going to end up happening is when I want to load a page of my address space from the disk into memory, it's going to take 8 disk I/O operations. And as you know, those are actually quite costly. So that, if the disk I/O operations are taking like 10 milliseconds and I need to do 8 of them, then that's like 80 milliseconds that I need to spend just doing handling a page fault. And so to reduce this seek time, we actually block consecutive groups of sectors together into larger blocks. And then the file system itself, instead of doing sector-based addressing, will do block-based addressing. So we have taken 8 sectors together to make 4 kilobyte blocks. And that way, when I'm doing on-demand paging, I know that all I have to do is a single read or write. And that's really nice because you're going to minimize your seek time. So the cost per byte to do that load will be very nice. Now, of those 4 kilobyte blocks, we logically divide the disk into those 4 kilobyte blocks, and then we are going to set aside a large number of those for the actual file data. Now, something to keep in mind is that files cannot share a data block. So if I have a file that is literally 2 bytes of data, it's actually going to consume a whole data block. It's not going to be able to share the leftovers of that data block with some other file. It's not to say there's never been a file system that did that. It's just that we don't do that. We're not going to do that. That's a management nightmare. So then we have these leftover blocks up here that we're actually going to zoom in on and just remind you of what we use those for. Those are actually for the file system's metadata. So we set aside some number of blocks to store our inode array. And remember that the inode is a 256 byte, or however many bytes we tell you, little structure that actually stores the metadata for the file. So things like file permissions, file types, file sizes, and it has a number of pointers to the actual file data. Now, there is a fixed number of inodes that can fit into this array, and yes, that does mean that there's a fixed number of files that will fit into this disk. We have here 80 inodes in our inode array, and our disk actually only has 64 data blocks. So even with 64 data blocks minus the 8 we use for the metadata, we have 56 data blocks for files. That means we can only have 56 non-empty files. So the fact that our inode array can store 80 inodes is completely fine, and you will find similar divisions on your disks as well. Now, to keep track of which data blocks and which inodes are actually free, instead of actually having to copy everything into memory and then check, what we keep are these inode and data block bitmaps, where each bit corresponds to one of the inodes and each bit of the data block bitmap corresponds to one of the data blocks. Now, each of these bitmaps is 4 kilobytes, which means technically speaking, they can store information for over 32,000 different blocks or inodes, and we have significantly fewer, but you can see here how we're still going to have to copy this into memory and search it, but since it's so much smaller, it's much faster. And then the super block, which is the first one, is actually going to store all of the information about the file system. Like, what is the size of the data blocks? How many data blocks are there? Where is the inode array? How many inodes are there? Where's the inode bitmap? Where's the data block bitmap? All of that information would be stored in the super block. And when we mount the file system, attach it to the computer is actually going to be able, the operating system is going to read that super block so that it can understand how to read and write to your specific disk. And obviously the values of these are going to change depending on the disk size. Because if I had a 14 terabyte disk, which I have quite a few of them, what you're going to find is that the 80 inodes isn't enough for a 14 terabyte disk, right? That just doesn't make sense. Now, just to remind you of how the inode is laid out, you have a bunch of attribute values. Those are the metadata. And then you have a bunch of pointers. So we can't actually, we don't store files on disk as contiguous blocks, even though for a mechanical hard drive, that's going to give us the lowest cost per byte in terms of I/O operations. The reason why we don't do that is fragmentation, and files could grow and files could shrink. So we kind of do something like paging, where we subdivide the file into a bunch of paged sized blocks, and then we have to keep track of where each part of the file actually lives on the physical disk. And we're not going to store a physical page table in the same way that we would for virtual memory, but what we do have is a number of pointers that point to different blocks. So we have direct pointers, which point directly to file data blocks, and those are going to be for if your file is really small, all you'll need is direct blocks. So you're always going to make use of the direct pointers first. If your file's too big for just direct pointers, then the inode contains a single indirect, which is also just known as an indirect pointer. And it is going to point to a block of pointers, and each of those pointers will point to file data. And then likewise, a double indirect is a pointer to a block of pointers, to a block of pointers to file data. And then a triple indirect is a pointer to a block of pointers, to blocks of pointers, to blocks of pointers to file data. And if you were to add up, and we showed you some formulas in the previous episode, and they're also posted in the file system guide on Piazza, is that the total file size that we can have for this very simple 256 byte inode, the total file size is over 4 terabytes. That's pretty impressive, because all we needed was these indirect pointers. Now the downside is that all of these pointer blocks are actually occupying data blocks on the disk. So your file size on disk and your file size, your actual number of bytes the file is occupying, file data occupies, are two different things. So your file data actually occupies the data blocks, and that will be how many bytes big your file is. But the total size on disk is going to be the sum of all the data blocks you use for the file data, plus you're going to have to include all of these indirect pointer blocks that you're using. So you're actually using a fair bit of extra space just to store this file. And depending on the system you are on, depending on the file system you're using, the file size on disk may vary quite a bit from the actual file size. Just to give you an example, and I know you can't see it on this screen here, but I'm opening this up on my Mac on my other computer that's sitting beside me. So I've got I've got a draft of my paper and one of the papers I'm working on, and it says my file size is actually 427,822 bytes, but the file size on disk is 430 kilobytes. So there's actually a few kilobytes difference between the actual file data and the size on disk. And then if I do this to my other machine, see, I've got the machine I'm streaming from is the one in the middle, and then to my left I have a Mac, and to my right I have a Windows tablet. So if I take a look at a PDF on my other machine, oh gosh, I don't really use Windows that often. So this file size for this PDF file is 428,380 bytes, and that's on Windows, and the actual size on disk is 434,176 bytes. So there's, again, a few kilobytes difference. Actually, it looks like there's a 6 kilobyte difference between the file size and the size on disk. So if you're wondering where do those differences come from, there's two places. It comes from all this extra data that you have to store, but it also comes from the fact that you can't actually share a data block with anybody. So, interesting details. Just closing out my stuff on my other machine here. If you're wondering why do I have so many computers, it's because I have the Windows tablet so I can actually follow Twitch if you have any questions, and then I have notes on my Mac, and then in the middle the Linux machine, of course, is streaming. And if I'm sitting here, I have two mice on my desk, and it's like, which one belongs to which computer? I always forget. All right, the last thing we left off with was looking at all of the disk I/O operations that actually happen when you, just trying to find the right slide, all the disk I/O operations that happen when you actually try to read or write to a file. And before we looked at opening a file and then reading from it. And what you can see here is when you open the file, you're passing it a string, and it's not so simple because you actually have to traverse that namespace tree to find the I number for the file so that we can refer to the file by the I number in all the subsequent operations, which means you actually have to open a bunch of inodes and read a bunch of file data in order to find that. So we have to traverse the tree, which involves opening and reading files. And so just to open this, we see there is actually 5 read operations. And then for each subsequent read operation, we have 3 disk IOs. And the reason why we have 3 disk IOs is we have to read the inode so that we know where in the file we are going to be reading from. And then we can get the pointer to the correct data. In this case, we're reading from the start of the file, so we're going to it's just a single read operation to read that block in, and then we write back to the inode because we actually accessed the file and we want to let the file know at what point it was accessed. So reading and writing from a file is actually very disk IO intensive because we have to do all of these different reads and writes. So I want to show you one more example of this. I'm going to switch over here. And this is to create a file and then actually start writing to it. And we're going to try to create the same file that we were just reading from. So in create, we have to first find the directory where we want to put this file in, because that we need to find an inode and we need to write the I number to the directory. We need to create the hard link for this new file. So we're going to have to traverse our namespace tree again. So we read the root inode, which gives us the pointer to root's data. We read root's data to get the I number for foo. Then we can read foo's inode based on its I number, and that gives us a pointer to foo's data. Now, upon reading foo's data, we find that bar is not present, and so we need an I number for bar. So then we have to read the inode bitmap. We are going to find a free inode. We are going to take that to be our inode, and then we are going to update the inode bitmap and write it back to disk. And then I can add the hard link for foo bar to directory foo and whatever I number I actually just discovered. Then this is the part that confuses people a lot. Then before we are done, even though we have created the hard link, now we actually need to create the initial inode. And you'll notice we're not just writing the inode, we read the inode before we write it. And the confusion here is that, why are we doing that? Why do we have to read the inode before we write it? The reason is the inode is smaller than a block. An inode is only 256 bytes in this case, and I cannot do a sub-block write or read. If I want to write a small region of a block, I actually have to read the whole block in, perform the write in memory, and then write the whole block back. So I'm going to read in bar's inode, and what that's really saying is I'm going to read the data block that contains bar's inode, and then I'm going to write bar's inode to the data block and then write it back to disk. What we're going to be doing in writing the bar inode is we're going to be clearing it out, setting all the pointers to null. We're going to set the size to 0. We're going to set the permissions, the ownership, the date created, and all that other metadata. And finally, since we updated the directory of foo by adding a hard link, we are going to write to foo's inode to indicate it was modified at this time. So in order to just create the simple file, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 disk IOs. If each of those disk IOs takes 10 milliseconds, that's 100 milliseconds. That is a long time just to create a file. We haven't even written any data to it. Now, if I want to start writing data to it, since I'm going to start writing data at the beginning of the file because it's brand new, I will be accessing that data, those data blocks through the direct pointers. So in order to do the write, I have to first read in the inode so that I know if I am going to need a direct pointer or a single indirect or so on. And also because I'm going to be updating the inode. After reading in bar's inode, I realize the file is empty, and so if I want to write a block of data into this inode, I need to get a block of data. And so I have to read the data bitmap, and then get a block of data, and then take it, update the data bitmap, then I can actually write to that data block, and then I can update bar's inode to indicate the new file size, and update the pointers, and access modified time, and so on. And each subsequent write, you'll notice we do the same thing. Now, these were all direct pointer writes for fresh data. If I ran out of direct pointers, then I would need to use the single indirect pointer to write file data. If I've never used the single indirect pointer before, then instead of getting 2 data blocks or 1 data block from the bitmap, I have to get 2. And then over in here, I would actually, instead of be writing just the data block, I would also have to write the single and direct pointer block. So the number of reads and writes is going to increase as the file size increases. But the nice thing is, even if your file is 4 terabytes, at most, you're going to have to read the inode, 3 levels of pointer block, and a file data block. So it's like 5. It's not too bad. All right. Now, I'd like to do a little sample problem with you all. Let's just bring it up here. I gotta find it. Path trans. So this one is called Path Trans, and you can find it again on Piazza in the archive. And what we want you to do is to write a piece of pseudocode that takes a path, and using the functions provided here is actually going to find and return the I number to the user. So we can do this. It's actually a fairly straightforward piece of code to write. And normally I would use my pen entry system, but to be honest, my writing's pretty messy, so let's do it in VI instead. Okay. I'm going to move things around a little bit so I'm not like knocking all my mice on the floor and my power switches and all those things. I'm not actually going to save this file, so I don't really care what it's called. So here's what we're going to do. And again, you can follow along with the PDF that's posted. What we're going to start by doing is, so we have this function. It shows up pretty small. Let me increase the font size a bit more. There, nice and big font size. Hopefully those of you watching now can actually read that. So we get a path. And what we're going to do is we're going to set the initial I number, to the root of the file system's I number. Now, the root of the file system's I number is actually going to be known and specified in the super block because it's a piece of information you need in order to actually traverse this namespace tree. Now, the other thing I'll say is that root isn't always 0. Sometimes it's 2 because the first 2 inodes are often actually used to keep track of bad data blocks on the disk so that you're not trying to read or write to them. But we're going to assume for this problem that root is 0. Then what we're going to do is we're just going to have some int I, and then for each of the components in our path, we are going to do something. Now, you'll notice we're doing from 1 to number of components instead of 0, and that's because the 0th component of the path is going to be root. So the first thing we're going to do is we're going to make sure that the current position we are at is actually a directory. Because if it's not a directory and we have more things to look through, then this isn't a valid path. So we're going to use the, if it is not a directory, the current enum, we're going to return invalid. This is an invalid path. Otherwise, we are going to search this directory for this component of the path name to try to find this component's I number. So use dsearch in the current directory for the ith component of the path. Now, it may be present and it may not be present, so we need to check that. So if inum is less than 0, it means we didn't find it. Then we're going to return invalid again. Otherwise, we have a valid path number, and we're either going to stop looping here because this is the end, or we're going to continue looping and going through each of the path components. And at the very end, we just return the I number. So that is one way that we can do it. And this here, this little bit of pseudocode that I've written, actually corresponds to what we were just doing in the diagram that I can't find now. Clicking on the wrong button, and it's really annoying. There we go. There's the right button. So all of this, when we're opening and reading the file, that code that we just wrote actually corresponds to this exact thing. All right, so that's a fun sample problem to do. So let's move on then in our notes. I think that we have a pretty good understanding. A couple things I wanted to say, because they're not actually posted in this, is how would you delete a file? This is going to come up in some of our discussion in a minute, but deleting a file is interesting because, as I've mentioned before, when you delete a file, you don't actually delete the data. When you delete a file, you remove the hard link, and you mark the inode as free, and you mark the data blocks as free. But the actual file data that's stored in the data blocks, you leave it alone, unless you're doing a secure delete, in which case we would actually delete that data. So if you were trying to figure out how many disk IOs there are for a file delete, it's actually going to be identifying all of the data blocks that are used by the file, reading in the data bitmap, and then marking them all as free. And you'll be doing the same for the inode bitmap, and that's about it. So it's much, much faster to do deletes that way than to truly delete the data. By the way, things like quick format. Do you know how quick format works? Let me tell you how quick format would work. Quick format reads in the data block bitmap, reads in the inode bitmap and the inode array, and flushes them all out. And in fact, it may not even read in the inode bitmap or the inode array. The fastest way to format your disk is to take those two bitmaps and mark everything as 0. That is, mark everything as free. But all the data is technically still there, which is why you should never use quick format, because your data is still actually there and it's totally recoverable. Don't do it. All right. So I'd like to talk now about a different kind of file system. So we've talked about very simple file system, VSFS, which is kind of based on Unix file systems like ext1 and ext2. And there are alternative approaches to doing file systems. For example, there's one known as chaining, and an extension of it is external chaining. Now, they call it chaining, but I want to give you a challenge you to just call it a linked list. Let's store files as a linked list. Let me show you what I mean. So with chaining, we still have what's known as a directory table. And the table is going to be able, kind of like an inode array. And instead of having all these direct, single indirect, triple indirect, blah, blah pointers, we have just one. And that one pointer is going to point to the first data block of the actual file. So for the purple file, this block here would be the one that the directory table points to. And then what happens is the last 4 bytes of each of these, or the last few bytes of each of these data blocks, is actually going to be the pointer to the next block of the file. So if you want to read the last block of the file, you actually have to read every single block of the file in, so that you can literally traverse the linked list of file data. And that is even if you were to seek to the end of the file and then try to read from the end of the file. In order to do that, we'd actually have to read the whole file in sequential order to find the end of the file. So for chaining, if you're always doing sequential reads and writes, this works out and the performance is pretty good. Implementation, super simple. Extra file data used, not that much, because each of these little data blocks simply has one pointer to the next block. So like 4 bytes of each of these data blocks is reserved for system information. So we're not using a lot of extra data space to store data structures and so on and so forth. And for sequential reads and writes, it's actually perfectly fine, pretty fast actually. And in fact, this kind of file system is great for if you're trying to just watch movies and you're not like trying to skip ahead or back in movies or media files, because that would be sequential file I/O anyways. The downside, of course, is that if we're using chaining and we have random file I/O, it's going to be really, really bad, because if I want to randomly access different parts of the file, I actually have to read in all of the file up to that point. It's kind of slow. Now, there is a small improvement of this, and that's external chaining. And the idea is we want to take the chain of pointers and put them in an external place called the file access table. So that instead of having to read in the actual file data to traverse the chain, I just have to read in this smaller data structure to traverse the chain. And this is actually the FAT, or file allocation table, file system that Windows used up until, I want to say, the early 2000s. But even still, like if I were to look around my desk here, and I know you can't see it, I actually have like 2 shelves above my head. I have a whole bunch of disks and cameras and things up there, and all of the file systems on every single one of those little camera disks, they're all FAT file systems because they're so easy to work with. So even though FAT is massively outdated, it is still used today for pretty much everything. It is probably the world's most supported file system because it's so simple. So what the external chain does is essentially, it's just a very small data structure. And I mean really small. It can store like a couple integers. And all it does is it says 2 things. And to be honest, it can actually store even 1 integer, because you can simply map the index of this to the index of one of the data blocks. So really all of this external chain does is store the index in the external chain of where the next file block will be. And then you can map between the external chain index and the data block using a very simple function. And so in order to traverse the file this way, instead of having to read all those 4 kilobyte blocks of file data, we just have to read in this really small external chain, which is significantly less, in order to actually do file reads and writes. Now, it's still not... Sequential access is still going to be significantly faster than random I/O, because sequential access, we are only going to have to, we know where we are currently, so we just go to the next one. But if we are doing random I/O, we are going to have to bounce around a lot in the external chain. But the performance isn't, it is a significant improvement over the other one. Now, there are some restrictions with the FAT file system. So up until Windows 95, I believe we were using FAT16, and that had a maximum file size, I think, of 64, 65 kilobytes. Or maybe it was megabytes. Yeah, it was megabytes, 65 megabytes. And then the FAT32 file system, which is kind of the end of the FAT file systems, has a maximum file size of 4 gigabytes. So it's really interesting, because if you go to like Canada Computers and you buy like a little memory card for your camera, or if you're buying, you know, a little USB device, the default file system on these is actually FAT32 because of it's compatible with everything. Like even the TV thing that I installed in my car speaks FAT32. And in fact, it's all it speaks. And so when I'm putting media files on it so that my kids can watch TV in the car, we have to make specialized downsampled versions so that their file size will be less than 4 gigabytes. There is an extension to FAT32. It's called exFAT, and exFAT actually does support larger file sizes, but not every device, not every system will actually support the exFAT file system. So I want to say, if you're not sure of what file systems are supported by a particular device, you should use FAT32, because it's probably the most likely one to work. Everybody knows how to read and write that, even my car. All right. So what I'd like to do now is kind of talk about file system design. There are other file systems, by the way. We've only talked about 2 physical file systems, 3 maybe. And you obviously in your reading assignment, you're reading about a 3rd one, which is the log structured file system, which is kind of what Amazon S3 is based on and a lot of other modern file systems. So hopefully you will find that interesting or useful. But let's now take a step back from particular implementations of physical file systems and ask ourselves, if you wanted to design your own physical file systems, which there's nothing saying you can't. I mean, if a couple of people from real time can design their own real-time OS for actual world, then I don't know why we can't design our own file system. But what kind of decisions would you actually make about in order to design that file system? And the thing I want to challenge you is when you're trying to design something like an operating system, when you're trying to design something like a file system, you really have to think about who's going to use this? What is the use case for what I am creating? Because certain use cases are going to have different demands. So for example, let's suppose you wanted to create a file system for a database company, a company that does all of their inventory is database files, and every record that is stored as an individual file, and every record is less than a kilobyte in size. Except there's like trillions of them. How would you design a file system for that particular use case? Well, for one, if you know that the size of the file, each file, is less than a kilobyte, then a block size of 4 kilobytes means you would be wasting 75% of your disk space. So you might change your block size to be 1 kilobyte, and that way you are minimizing the wasted space on disk. Furthermore, your inode array is going to have to be huge because you know that you're going to have so many different files. And then the inodes themselves could be smaller because if every file is 1 kilobyte or less, then each file occupies only a single block. Now you might be like, well, then I just need one direct pointer. But you have to think about the future too. It's plausible that the size of these records could grow with time. So maybe you want to support slightly bigger files. So maybe you'll put, I would personally put in 8 direct pointers and 1 single indirect. Even though we probably will never use that in the next 5 years, 10 years from now, I won't have to change my file system when my record entry size changes from 1 kilobyte to 4 kilobytes. So you can see you want to future-proof it somewhat, but still keeping in mind what you have right now. On the other side of the fence, sort of my research side of the fence, is dealing with film industry. And in the film industry, one of the big tasks we do with disks is actually use disks for long-term archives. Okay, to be completely honest, we don't use disks for that. Film archives are actually stored on magnetic tape because it's cheaper per byte and because it's not something you're going to be reading and writing all the time. But let's suppose we used hard drives for this instead of tapes. So if I were to try to create a file system for archival of film footage and film assets, I'm going to be thinking very differently from the database case. Number one, I have to think about how much data, how much footage is actually captured in a day. It's a lot. If memory serves me, so the newer RoboCop, let me see when that was released. I don't even remember when that was released. I don't know if you've seen it. So it was 2014. So the 2014 RoboCop was actually filmed in Toronto. And my recollection of when they were filming that is they were producing about 1.5 to 2 terabytes of footage per day. And they keep it all. And maybe like, why would you keep all that footage? Well, you don't know, even if you have like 30 takes of the same scene, you never know which one of those takes you're going to end up using the day that you've captured it. It may take you a month or two to finally decide which of those takes is the best one. And you might actually end up combining different elements from that, from one take and another take to get something that's even better than any of the individual ones. The other thing is there are maybe takes you do for scenes that that don't appear in the final movie, but we'll still keep them. And we keep them because, 5 years later we release the extended edition. Well, where did you think that footage came from? It came from the archive. That was all captured originally. We didn't go back out and shoot it. That was original footage that we've just kept. So the film industry keeps all of this stuff. The file sizes tend to be a lot bigger. Not 1.5 terabytes, because, that represents many, many different cameras. That represents just a lot of stuff. But if we were trying to design a file system for that, we would probably use a larger block size, because we know that the files are all really big. The files, I have a few shots from several films on my laptop here, and I think the smallest shot I have is about 6 gigabytes. They're big files. And so I would create a much larger block size. I might actually have my block sizes be a megabyte, because even assets, so even digital assets, things like Thanos isn't actually, yes, there's a dude who's doing some motion capture to animate him, but there's not actually this giant purple guy walking around the earth. That's not real. That's all CG. Well, that asset is not that small. It's going to be pretty big. And so I would, for this particular file system, I would use larger block sizes. My inode array would be smaller because because the files are bigger, I wouldn't be able to fit as many of them on the disk. So I would have a smaller inode array, larger block size because my files are all bigger. And then I would focus on, in my inode, balancing the direct and indirect pointers in such a way to try to minimize how much extra space we have. And if I was doing a file system for just the purposes of film archiving, I would probably actually use a chain style file system. So either chaining directly or using an exFAT system, simply because I know that for an archival footage, access is after finding the initial beginning of the file, access is going to be sequential from that point forward. And I would know that the extra data is minimized for that system. So there's lots to think about when you think about designing a file system. Lots to think about. All right. So the last kind of section of the official slides here is to talk about problems that are caused by failures. So I'm sure some of you have actually encountered this in your life at some point, but if the power goes out, sometimes your computer doesn't quite come up correctly again. I know, for example, the power went out before our last episode, which was Thursday's episode of last week, and my desktop didn't come back up properly. Now, it wasn't actually a file. Kind of was a file system issue. More of a BIOS issue than anything else. But in the old days, before we used journaled file systems, and I'll explain what journaled file systems are in a minute, if the power went out, your file system could actually get into a really bad state. Let me explain how this would happen. If you were trying to delete a file and your power went out, when your power comes back on and the computer gets rebooted and starts back up again, you were in the middle of deleting a file. So you may have marked the inode as free, but maybe you haven't marked all the data blocks as free yet. But the problem is that operation of deleting the file has been lost due to the power outage. And now what you end up with is you have a free inode. That worked. But there's a bunch of the file's data blocks which are actually marked as in use, but since there's no inode that actually points to them, they're no longer usable by the file system. So not only can you not access them again, because you don't know what file it belongs to, but number two, you won't be able to free them because they're orphaned. So, and when I was a kid, this happened a lot. So I grew up in the country. I had a really our power was awful, and my computer ran FAT32 as a file system because this was pre-journal days. And when we had a power outage, every time you rebooted the computer, something called ScanDisk would run. And maybe you've never seen ScanDisk before. Let's find it. Find images. Of course, it's going to bring up SanDisk, not ScanDisk. So that's Windows setup. Let's look for ScanDisk, Windows 95. Oh, I found something, but it's not what I was looking for. Let's try Windows 98. There it is. So what you're seeing here, this little ScanDisk program, and let's make it bigger so you can actually see it. So when you'd reboot your computer, this would come up. And you can manually start this up as well. But when you'd reboot your computer after a power outage, this little tool called ScanDisk would come up. And what this tool does is it scans your system, your file system, and it looks for data blocks and pieces of the file that are orphaned. And it tries to fix them. So if it finds a data block that's marked as in use, but there's no file that's actually using it, then it would actually be able to clean that up, and it would mark that data block as actually free. The interesting thing is, it sounds like it repairs everything. So doesn't. And in fact, after so many crashes like this, you would actually find that the file system became so corrupted that it almost became unusable, and you'd actually have to start fresh. I mean, hard, low-level format, start all over again. What we really want is for our file systems to be what's known as crash consistent. So if there is some kind of restart or failure during us reading or writing or modifying the actual file system in some way, then we want to make sure that when the computer comes back up, that doesn't negatively affect the actual structures that belong to the file system implementation. And that's precisely, and by the way, so ScanDisk isn't unique to Windows. There are similar things like fseek in Linux that were used, and Unix and BSD that were used to essentially do the same thing. So it was used to repair inconsistencies. But what we do now to solve this problem is we use what's known as a journal file system. And we've been using journal file systems for close to 20 years, I want to say. I'm trying to remember. So I know I used RiseRFS before I used ext3. RiseRFS being a journaled file system as well. I didn't run a lot of Windows hardware. So what a journal file system is, and by the way, it's not a new idea, is it doesn't perform changes to the file system's metadata, so the inode array, the data block bitmaps, directly. What it does is it has a journal, which is like a cache of all of the metadata changes you want to make to the actual file system structures. And that cache is a log or a journal. And then periodically, you take the journal and you actually perform all of those operations. The idea is, and then once all of the journal things have been written to disk or actually performed, then you can clear out the journal and start again. Now, how does this save you a little bit? Well, what's going to happen is if a power outage happens or the system fails, you are going to have something like an incomplete entry in the journal or a missing entry in the journal. And those ones there's not much we can do about. But since we don't clear the journal until after we've actually performed all the operations, if we get interrupted during one of those operations, when we reboot the system, the journal still exists, so we can just go back through the list of things we wanted to do and check whether they have actually happened or just redo them. So it helps you actually recover from failures. it is not a perfect system. So for a long time, my RAID arrays ran NTFS, or my backup systems ran NTFS. And I want to say maybe once a year, we would have sufficient failures due to power outages that the journal, we would run into a situation where the journal wasn't able to recover it. And so we'd have to reformat the disk, usually about one disk a year. Since I've moved, and that was NTFS. Now that I've moved over to ext4, I actually don't think I've had to format anything. Anyways, I also have had significantly less power outages because I don't live in a student housing apartment anymore. Now I actually have a house and we have much fewer power outages. But either way, I haven't actually had to do any reformats with ext4 yet. So that's what journaling does, is we're just going to keep a log of all of the metadata changes we want to make, and we keep the log completely intact until all of the operations have completed, so that if we are interrupted, we can actually redo them all and not miss anything. So that's really nice. But if a power outage actually occurs when you're like writing to the journal or log, then obviously some of the operations are going to be lost. So it is not perfect, but it is a significant improvement over what we used to do. All right, so we've got about 10 minutes and 15 minutes. And what I'd like to do is another sample problem. And it's one of my favorites, although I don't think it's anybody else's favorite, just probably mine. This one I'm actually going to need my tablet for, so I'm going to fire that up. Here we go. So let's open up this. And then I want to do this one. This is called File I/O. So what we're going to do with this problem is we have a really, really big file and we've already opened it. So we already know its I number. We already have its file handle. And it's a really big file. We're going to assume it's like terabytes in size. And I want to perform some operations on the file. So I'm going to do an lseek. And then I am going to overwrite 1,000 bytes of the file. And then I'm going to read 1,000 bytes of the file. And we are going to make the assumption that the file is so big that all of this data actually exists. The question is, if our file system uses a block size of 1 kilobyte, and our inode has 9 direct pointers, an indirect, which is just a single indirect, and a double indirect, how many reads and writes are going to happen for each of these operations if we have a cache and if we do not have a cache and the cache is initially empty? So let's actually take a look at this. Now, the one thing I want to say is that this particular problem, there's a fair bit of information you need to figure out first. And that is you need to figure out how the file system is actually laying data out. Let's bring up the little pen thingy here. You know what? We're not going to do that. So the first thing I note is that block size is 1 kilobyte. Which is 1,024 bytes, which is also equal to the power of 10. All right. Now, my pointer size, you'll notice we didn't specify in the problem, but if we don't specify the pointer size, you may assume it's always 4 bytes. So my pointer size, I'm getting a little lag here, is 4 bytes. It's really annoying when there's a lag. When there's a lag, I can't write nicely. Let's see if I can update it here. All right, so I've got this 4-byte pointer. So in order to figure out the layout of this inode and how files would be laid out on disk, I need to know how many pointers fit into a block. So pointers per block is going to be how many pointers fit into 1 kilobyte. So I've got 1024 bytes divided by 4 bytes, which means that my blocks can fit 256 pointers each. So the next thing I have to ask is how much memory is accessible from each of those pointer types. So we have 9 direct, pointers, and that is going to give me access to 9 times 1 kilobyte. So up to 9 KB. Now that in itself isn't so useful, but what is useful is if I showed you the range of bytes that this actually occupies. And this occupies bytes 0 through 9216. Notice the bracket change there. Okay. Now, the next thing I need to know is which bytes are accessible from the single indirect. So it's going to start at byte 9216, and it's going to go to 256 times 1024 plus 9216. And I know from my problem, which I'll just go back here, that I'm going to be looking at byte 10,500 to 11,500 to 12,500. So I can see that this fits clearly within the range of bytes accessible from the single indirect pointer. So we're actually going to ignore this double indirect pointer because we don't need it. All right. Now I need to know where in the single indirect pointers blocks, which particular blocks or pointers am I actually going to access? So let's break up our pointer block. Oh, that's really annoying lag. I think I have like a lot of Bluetooth interference, which is actually causing like the Bluetooth on the pen system to go really, really slow. Okay, we seem to be back. So the first pointer, uh-oh, the lag is so bad. Maybe we can reset the device. Okay, let's check it again. Seems to be back up. So the first pointer will go from byte 9216 to byte 10240. Okay. Then the second pointer goes from byte 10240 to byte 11,264. And then the third pointer points to data from bytes 11,264 to 12,288. I'm sorry I'm writing kind of funny. It's just to make it so it's as clear as possible. And then the fourth pointer goes from 2288 to 13312. Okay. So our LSEEK operation, let's use a different color here. It is looking at going to byte 10,500. So how many reads and writes is that? It is 0 reads And it is 0 writes to disk. And the reason why it's 0 reads and 0 writes to disk is because seek doesn't touch the disk. Seek only updates the position of the file pointer as stored in the file handler table or file descriptor table inside the process. It doesn't actually validate that that belongs to the file. So our lseek operation does nothing in terms of disk I/O. Then we have a write operation. The write is 1,000 bytes, so it's going to start at the seeked position, which is 10,500, and it goes to 11,500, which means that my write starts here and my write ends here. So that is my write operation. So assuming my cache is initially empty, this is what I'm going to have to do. I have to read my inode. I have to read my pointer block. And I have to read, I'm going to label these A, B, C, and D. I have to read data block B, and I have to read data block C. Then I have to write block B. I have to write block C because I'm doing partial updates to these blocks. Because we start writing in the middle of this block, I can't just write to the block directly. I have to read it in, update part of it, and then write it, the whole block back. So I write B, and the same as C. I'm going to write C, and then I have to update the inode, so I write the inode. And that's because nothing was in the cache. So I'm going to put each of these things as I perform the operations. They're all going to go into the cache. Okay. So that's 4 reads and 3 writes. Now the subsequent operation is a read. Oops, pen's falling apart again. I should really glue this thing back together. So the read is going to go from byte 11,500 to byte 12,500. Now normally we would have to read the inode, read the pointer block, read block. So where does this operation happen? So this operation actually starts in the middle of C and it finishes in the middle of D. So that's our read operation. So normally we would have to read the inode, read the pointer block, read block C, read block D, and then write the inode. But because block C and the pointer block and the inode are in the cache, we don't actually have to read those. So all I'm going to do is I have to read D because D is not in the cache. And then I have to write the inode to update the access time. And we get all of those other operations are not disk IOs because they're in the cache. So a cache can really improve the performance of anything that you are doing with a file system. And that is why we have things like this persistent RAM, the Intel Optane, is so that we can actually have a persistent cache. That's pretty useful. Excuse me. All right. So those are our sample problems for today, and that is actually the end of file systems. In our next episode, we're going to talk briefly about virtual machines, which also serves kind of as a review for the course. And then in our final episode, we're either going to look at networking or how to design an operating system. If you have a preference, let me know on Piazza. I'll try to create a poll for that. So we will talk to you on Thursday, and I hope you have a lovely day.